we need to talk about conversion of coordinates from one system to another, either rectangular with x and y to polar with r and theta, or vice versa. And this is a skill that you guys just need to get so good at, because we're going to be using this a lot going forward. Now, what I'm covering in this video is an example of going to rectangular coordinates. Okay, that's what we're talking about first. Then I'll do an example of going to polar coordinates. And then I'm going to get to a third example using kind of a weird situation. We're still going to polar coordinates, but it's going to be a little dicey. Okay, so depending on which problem you're looking at, you may want to focus on the beginning of this video, the middle, or the end. But that's the order I'm going to be going through. So let's talk about the rectangular coordinates first. And you'll see here I've got these equations. We're going to use these a ton. Burn these into your brain. Every time you're looking for an x-coordinate, you can just literally plug in r and theta in here, and that'll give you the x-coordinate. It's very nice. So, for example, I'm going to do this one. Let's see. Give me some room here. X equals, and I'm focusing here. X equals r. Now, r is 2 times the cosine of, what's that angle? Negative 4 pi over 3. Not the most convenient angle, but that's what we've got. And if you're thinking about the unit circle, right, kind of looks like this, and negative 4 pi over 3 is going in the negative direction all the way over to here or so. Well, I would prefer to think about that as 2 pi over 3. So you can replace this with a similar coterminal angle, if that makes life easier for you. Right, these are equivalent. Or what you can also do is you can use your old trig even odd identities and recognize that the cosine of negative 4 pi over 3 is the same exact thing as the cosine of positive 4 pi over 3, because cosine is an even function. So whichever way you like to do it is fine. But the important thing is you have to somehow get to this point where you say, aha, I'm located right there. That's where this is. And of course, it's a radius 2, not radius 1. So what's this going to be equal to? Well, this is 2 times the cosine at that point is negative 1/2, because it's to the left. So this becomes negative 1. So there we go, negative 1. And the y coordinate at that place is just 2 times the sine of that angle. Negative 4 pi over 3. So I'm looking at that dot again, and I say, oh, that's the tall one. That's it's not negative 1/2. It's going up by radical 3 over 2. So the 2's cancel out, and you just get radical 3. Okay? So this is the general framework that you're going to use for all of these polar coordinates, changing them into xy coordinates. And I could go through each one of these. It's not really necessary. Nothing is going to change as you work through these examples. Even when you have like a negative radius, when you just multiply your trig value by a negative number, and it'll all work out. So moving on, let's talk about changing rectangular coordinates into polar coordinates. This is where you're going to start to see, well, things are going to be a little strange, but just hang in there. So let's take a look at this first one. Okay, and I want to remind you of the equations that we have for r and theta. Okay, here's one of the equations. R squared equals x squared plus y squared. And the other equation, tangent theta equals y over x. So we're going to use both of those. Let's use the r equation first. R squared equals x squared plus y squared. This is problem number 1 that I'm doing. So I say, okay, fine. X squared, what is that? Well, that's 25 over 4. And y squared, more complicated. That's 25 times 3 over 4. Why am I doing times 3? Well, I square this part, the 5, and I square that radical 3 also. So this turns out to be 25 fourths plus 75 fourths equals 100 fourths, which is just 25. So if r squared is 25, that means r is 5. So that's nice. Now, how about theta? Well, tangent of theta equals y over x, right? Y over x. Okay, well, y is not pretty, 5 radical 3 over 2, and x, not very pretty either, but we remember how to do division of fractions, right? That's from a long time ago, but we can rewrite this, and I think this will make it much easier. You got 5 radical 3 over 2 times 2/5. And now look, the 2's, 5's, cross out. All that's left is a radical 3. So hopefully you still have your tangents memorized from unit circle. Where is the tangent of theta equal to radical 3? I'll just draw these quick here to remind you. That right there is where tangent is 1 over radical 3. This right here is where tangent equals 1. This right here, we're getting pretty tall now. That's where tangent equals radical 3. Okay, over here it was 0. Over here it was infinity, right? That's a DNE. So those are your tangents in the first quadrant. And I'm looking at this and saying, okay, well, looks like I am right here. That's pi over 3. Okay, now you might be thinking, well, that's not the only place where tangent is equal to radical 3. There's another place too, down here. How do I know that's not the angle? Pause the video here, see if you can noodle it out. The reason is, we look at the xy coordinates. See, x and y are both positive. That tells me I am in the first quadrant, not the third one. And we're going to need that. It's not a trivial point. So, for example, on this next example, I'm going to put this in blue so we can distinguish it, because I think we're going to get a little crowded here. In this one, what is 3 radical 2 over negative 3 radical 2? Okay, in example number 2, tangent of theta equals y divided by x. Okay, now that's equal to negative 1. Everything, just about everything crosses out. So where's tangent equal to negative 1? Well, 2 places. Here and here. Which one's appropriate? Well, if x is negative and y is positive, where is that? That's negative x, positive y. I'm over here. Okay, this is a quadrant 2 angle. So in that case, I would use 3 pi over 4 as my theta. And the r value you can calculate. Those are usually easier. That's just Pythagorean's theorem, right? X squared plus y squared. So now let's come down here to the third example and see what the big deal is. Because if anything, these numbers look nicer, right? There's no square roots. But take a look. I'll pick on, here I just did quadrants 1 and 2. Let's pick a quadrant 3 angle, right? I can see right away this is quadrant 3 because it's negative x, negative y. So let's go through the process. I would say r squared equals negative 1 squared plus negative 5 squared, and that's equal to 26. So that means r is the square root of 26. Well, that's not pretty, but it is a number, so don't worry about it too much. Tangent is where this is going to get a little complicated. Tangent of theta equals y, which is negative 5, divided by x, which is negative 1. Okay, well, that's 5. Great. I don't remember where tangent of theta equals 5 on the unit circle. As it happens, it's up here somewhere, and it's not a pretty angle. We don't have that one memorized. So what we're going to do for problems like this is you just say theta equals arctangent or inverse tangent of 5. Okay, and that's your answer. That's as good as we can do. Now, there's a little bit of a hiccup here. What did I mark on that circle? Oh, I marked quadrant 1, right? Well, is that correct? Take a look here. This is quadrant 3. So if you put, and this might be the mistake if you're looking for help in this video, this might be what went wrong. If you put inverse tangent of 5, the calculator and the computer too will think you're talking about this one right here. We need a way to say quadrant 3 right here, because that's also inverse tangent of 5, but it's not what the computer will reach for. So you have to think about how to turn this angle into this one. What do we need to add to it? Right? Well, that's just plus pi. So instead, I'm going to say, well, that's not right. Here's our answer. It's inverse tangent of 5 plus pi. Okay, and that's what the computer is looking for. In other words, you need an awareness of quadrants. And keep that in mind.